Finally, we want to see the situation where we have two objects that are both moving. All of the other derivation that we've done thus far has been for one object, an incident object that's moving at a target object that is at rest. Now we want to see what happens if both of them are moving at the same time. And so we'll follow the same pattern. We look at the total momentum before the collision, the total momentum after the collision. They'll hit each other, they'll exchange some energy, but conserve their kinetic energy. So they'll have different velocities after the collision than they had before. They'll have different kinetic energies after the collision than before, but the total momentum before the collision will equal the total momentum after the collision, because momentum is always conserved. Again, because we're assuming a perfectly elastic collision, the total kinetic energy after the collision equals the total kinetic energy before. As before as well, we'll start by throwing out the factors of 1/2. They just get in the way in this situation, and we'll approach this a little bit differently. What we're going to do is move all of the velocities for object 1 over to one side. We're going to move all of the velocities for object 2 over to the other side. And so when we rewrite that, we're going to see that we have and for reasons we'll see in just a second, we're going to change the order here so that we have the same pattern. We're going to do that by factoring out a negative m2. And so that'll give us a positive v2 prime and a negative v2. Similarly with we'll also factor out the m1 term. So this is one of the relations that we're going to use in just a minute. We're also going to look at the conservation of kinetic energy, where we have we'll do the same thing here. We'll factor out a negative m2 and we'll factor out an m1 out of that term. This will be our starting point. This is our conservation of kinetic energy. We see we have a difference of 2 squares, and we are going to go ahead and factor those. Now what we see is that m1, negative m2 times v2 prime minus v2 is equal to m1 times v1 prime minus v1. So if we divide the left side by negative m2 v2 prime minus v2, and we divide the right side by m v1 prime minus v1, this term is equal to that term because we found that they're equal to each other because of the conservation of momentum. And so if we divide this side by one term, this side by the other term, we're doing the same thing to both equations. We're dividing both sides by 2 different values, but 2 different equal proportional values, equivalent values. And so we can go ahead and cancel and we can eliminate everything that we just canceled. And so now we have one more relationship here, that v2 prime plus v2 must equal v1 prime plus v1. And so now we have two equations and two unknowns. The v2 prime, v1 prime are our unknowns. So we're going to return to this initial relationship. But if we want to solve for v1 prime, for example, we have to eliminate v2 prime. How can we eliminate v2 prime? We can come over to this other relationship, and we can say that v2 prime is equal to v1 prime plus v1 minus v2 if we move v2 over to the other side. If we plug that in over here, we've replaced v2 prime with the expression we found from the conservation of kinetic energy. Now we will distribute our terms. And we want to solve for our v1 prime. So we want to put all the v1 primes together. This side is already positive, this side is negative, so we'll add this term to both sides. And that will cancel it out here, and we will eliminate that. We have all of the v1 primes on this side. We want to get rid of anything that's not a v1 prime, so we'll add that on this side, and that will cancel it out when we add and subtract it, and we will eliminate it there as well. Now we want to group our terms. And we can see that now when both particles are moving, we see that v1 prime depends on the masses of the particles, plus, or as well as the velocities of those particles. And we see that the arrangement of the masses in those factors is similar to what we saw before. We can do the same thing, but we will eliminate v1 prime so that we can solve for v2 prime. Same idea as before. We used this relationship. Instead of solving for v2, we solved for v1. We said that v1 was the other side minus getting rid of the v1 prime on that side. We replaced it here in this equation. We replaced v1 with our expression for V1. So we eliminate V1, now we only have V2 in terms of the masses and the initial velocities. So now we wish to solve for V2 prime. We will distribute again we wish to group our terms. We have a V2 prime here and a V2 prime there. We will move this term over. It's negative here, so we'll add it to the other side. If we add it over here, it will cancel out, and we can get rid of that. We also need to, now that we've grouped all of our V2 primes on this side, we need to get rid of everything that is not a V2 prime. So we'll add this term to cancel out its subtraction. We add it to this side, and we add it to the right side, and it cancels. This side is subtracted, and so is added, and so we'll have to subtract it from the other side. When we subtract it from both sides, it cancels and will go away. So now we will collect like terms. We have a V2 term and a V2 term that we will put together. And we have our V1 term that we'll leave by itself, and we will factor these terms on the right that have a common V2 prime. To solve for V2 prime, we have to divide by the other term, and we'll see that we see the equations for V1 prime and V2 prime. They depend only on the masses of the two incident objects and their initial velocities of the two objects that are coming together. We see a parallel in the layout of the masses. In this case, the idea is that we're looking at the collision from one side or the other side. And so there's a sense of perspective there where we can look at the collision from the point of view of one object or the other.